Hi everyone. As always, we started with the learning objectives that you have in here. Now remember that you can go through these and pause the video, but that I will show them at the end again so that we know what we've done. Now, before we start, it's important to review what we did the last day, because the notion of work and its unit is going to be very, very important for everything we're going to do after this. Now remember that the idea of work was very similar to what everybody understands by work, right? So I have a little box, and here I am, and then I push the box, and I bring it, I don't know, some distance away, d. Now, of course, the further I push the box, the more work that I did, right? The more tired I am, therefore I did more work. And of course, the bigger the box is, then the more work that I did. Therefore, what this tells me is that the more force that I have to do, the more work, and the more distance that I push something, the more work. Based on this very, very simple idea, we can just define work as just the force times the distance. And that will allow us to then talk about energy and a bunch of other stuff. But the concept is really, really simple. It's just I'm pushing something, and of course, the further I push, the more that I push, the more work that I do. Remember that the units of work are the joules, that are normally expressed as a little j, but the joules are not a fundamental unit, but they're a compound unit, and they're made of a Newton multiplied by a meter. So remember, 1 joule is a Newton times a meter. Every time that we talk about work and energy, the quantities are measured in joules. Never newtons, never meters, never seconds squared, always joules, both for work and for energy. Now, hopefully you remember that the other day I told you that energy is the capacity to do work. So for example, imagine that I have a box that's moving very fast. So here, let's make a little arrow. So this thing is moving very fast this way. Then I could use this to do some work, right? So for example, I could put a little box here, and this would push my box. And this would do work. So therefore it's clear that if something is moving, it has energy because it's capable of doing work. However, there's other things of doing work. For example, if things are high up, they can also do work. So imagine that I have this box now, same box, but instead of pulling it this way, I pull it up. Okay, so now my box is here. Now, what happens is that my box is not moving now, so it doesn't have this kind of energy, the one related to movement, but it has some other energy. Because if I now let it go, boom. Then, for example, I could put a little lever here, and then it would hit the lever here, and it would move whatever was in here. Therefore, the fact that it's high up means that it has some energy that I can release when I let it go. We call this energy potential. So the basic idea is that both if I'm moving or if I'm high up, I have some kind of energy, and we call this two types of energy, mechanical energy, because it's energy related to the position and movement of bodies, which is what mechanics deals with. Both of these types of energy, both the one that's related to height and the one that's related to movement, are capable of doing work. And in fact, they can turn into each other. So when this guy is high up and I let it go, it stops going faster, faster, and faster. So it stops having the energy that's related to its position, and it starts having some energy that's related to its movement. Now that we understand the basic idea that things can have energy just based on their position, we can start actually doing some calculations and finding exactly how much energy something has related to its height. And for this, what I'm going to take is this little box of mass m that goes up a certain height h, and remember that all the time this thing is being pulled down by gravity, right? So G, this is not the force, that's just the acceleration of gravity. Now, what I ask myself is, okay, how much energy does this thing gain when I lift it a certain height h? And remember that I told you that the increase in energy in something is the work that I do on it. Therefore, if I want to find out how much energy this thing gained going from here to here, I need to find the work that I need to do in order to lift this from here to here. And we did this the other day several times. Remember that work is the force times the distance. Now, in this case, the force that we need to do in order to lift this up is equal to the weight, right? If we can manage to do a force that's equal to the weight, we can lift this at a constant speed until here. So we need to overcome the weight. And how much distance are we moving this? Well, we're moving this is the distance h. So the distance is just h. Therefore, the work that we need to do in order to lift this a distance h is the force, which remember is mg, which is the weight of this thing. And remember that the weight is not the mass. The weight is mass times the acceleration of gravity, which is 10 meters per second squared. So mg, and then times the distance, which is h. So mgh. That's the work that I have to do in order to lift this box from here to here. However, now we know that this work turned into energy. And this type of energy is called potential. It's really energy that's related to position, so maybe it should be called positional energy, but it's not. It's called potential energy because, in a way, we're saying that this energy has the potential to become movement energy, which we will talk about later on. Therefore, I'm going to get rid of this symbol, work, and I'm going to call this potential energy, or PE. Therefore, I just showed you that the potential energy that a box gains when I raise it at a height h is its mass times gravity times the height. And this goes for any object that I lift a height h. So just like things that are high up can do work when they fall down, so can things that are moving do work, as I showed you before. So for example, if I put a little box here, when this bumps into it, it's going to move it for a while, and therefore I will have done work. Right? I will have applied a force on this thing for a certain distance, so I'll have done work. Now, the idea is that, therefore, this thing that is moving has energy, an energy that's related to its movement, and we call this energy kinetic energy because kinetic stands for moving in Greek. Now, what we need to think about then is exactly how much energy is contained in a certain box that's moving at a speed v. Now, the first thing that I'm going to do is to very rudimentary deduce a formula for this, and then later on I'm going to do this more precisely. Now, so the first thing that I think is, well, if this has a lot of mass, then it's harder to stop. And because it's harder to stop, it's going to move further. So if I put my little box here in the front, this is just going to keep moving for a longer time than if this was very small. Therefore, the more mass, the more energy, the more kinetic energy. So again, the more mass, the more kinetic energy. Now, the second thing that I ask myself is, well, is there anything else that has a relevance? And of course, it has to be the speed, right? If this is going really fast, it's going to be harder to stop, and then it's going to move our little box here in the beginning even more. So then, of course, the more speed, the more kinetic energy. And this gives us an idea then that kinetic energy has to depend on both the mass and the speed. Now, I'm not going to prove this to you yet, but what it turns out that the kinetic energy is equal to 1/2 of the mass times the velocity squared. Now, in order to understand this, the idea is that the velocity, why would we square it? Well, if it was negative, would this thing have any less energy? Well, no. It really doesn't matter where it's moving. All that we care about is that it's moving really fast. Therefore, we square it so that this thing is always positive. Of course, this depends on the mass, so the more mass, the more kinetic energy. And the 1/2 factor is something that comes out when you do deduce this rigorously. But if you don't want to see the rigorous deduction, you can just skip to the next slide. All you need to know is that the kinetic energy is 1/2 of mv squared. So what's going to come now is a rigorous deduction of why kinetic energy is 1/2 of mv squared. And again, if you don't want to see this deduction because you think it's going to confuse you more, just remember that the kinetic energy is 1/2 of mv squared and move on. Otherwise, keep watching. Now, what I'm going to do is to use the idea that work equals, as always, force times displacement. So imagine that I have a box of mass m that's still. And then I do a certain force F on it for a certain distance d. And I ask myself how much work I did on this box, because all the work that I did on this box will end up inside the box as kinetic energy. Remember that the energy that something acquires is equal to the work that I do on it. So the kinetic energy of this box will be equal to the force times the distance. So again, the kinetic energy of the box has to be equal to the work that I did on it, which is just the force times the distance. But of course, I don't want this in terms of the force and the distance. I want this in terms of the mass and in terms of the velocity. I want to get this thing here, not this thing here. So what I need to do is re-express things. Now the first thing that I find is that force equals mass times acceleration. Let me just zoom out a little bit so that we can move this. There you go. So if force equals mass times acceleration, then we can rewrite this as mass times acceleration times distance. And this is starting to look a little better. Now, of course, I don't want the acceleration as it is because I need the distance. So then I try to find some way of expressing the acceleration in terms of the distance or the velocity. Let's see what I can find. Well, acceleration is the increase in speed, remember? Increase in speed over the time. But it turns out that the initial speed of this box is 0, so the increase in speed is just the speed. So the acceleration is just v over t. And that makes me happy because then I have acceleration in terms of v. So now I can rewrite my formula and I have that the kinetic energy equals mass times the acceleration, which is v over t, times the distance. And now we're almost there. Now what I need to do is to express the distance in terms of the velocity. Now this time, careful, this guy starts still and ends at a speed v. So the average speed is not v, but v halves, right? It starts at 0, ends up at v, so on average it's gone at v halves. So the average speed is v over 2, because it's 1/2 of the maximum speed. So therefore the distance that this guy has gone through is just the average speed times the time. So d has to be equal to the average speed, which is v over 2, times the time. And now I have everything I need, because I'm going to plug this thing here into the distance. So again, kinetic energy equals mass times v over t, and now times the distance, which is equal to v halves times t. So times v over 2 times t, and you can see that the time disappears. So then we get 1/2, because they have these two here, then times m, and then times v, which is v squared, which is what I told you at the beginning. So this is a more rigorous deduction of the formula of the kinetic energy. Again, if you found this really hard to follow, you don't have to. All you need to remember is that the kinetic energy is 1/2 of mv squared. Now here's a really important concept that's going to come up over and over again, and that you are going to need if you need to solve the problems. And the idea that mechanical energy is conserved, and you will see this word conserved very often, also in the IB. Conserved means that it always stays the same. So however much mechanical energy I have at some point is going to be the same amount as I have at some other point. Okay, so imagine that I have a certain ball. So here's my ball, and my ball is at a certain height, and this ball is still. So it has a certain potential energy, okay? So it has some potential energy. But it has no kinetic energy because it's not moving. So kinetic energy is 0. And let's say that I let it drop. Then if I let it drop, what will happen is that at the end, the ball will be at the ground, so its potential energy will be 0. So how much will its kinetic energy be? Well, the idea is that the mechanical energy, which is this plus this, so the mechanical energy is the total energy, is equal to the potential energy plus the kinetic energy. And the idea is that this energy always stays the same. So whatever much I have here, that's how much I have here at the end. So if here I had 20 joules, then when this thing has fallen down, I still have 20 joules, I haven't lost anything. So if in this case the potential energy is 0, then all my energy is kinetic energy. If I had 20 joules here, I have 20 joules here. So this kinetic energy will be equal to the potential energy that I had at the beginning. How about in the middle? So how about when the ball is here in the middle? Well, here the ball has lost some potential energy, but not all, because it's still high up. And it has gained some kinetic energy, but not as much as here, because it hasn't fallen through as long. However, if I add up the potential and the kinetic energy here, I'm going to get the same as if I add them here or here. That is, the energy, the total energy is always the same. The types change. Potential turns into kinetic, or kinetic turns into potential. But the total, adding them both up, is always the same. So the total energy is the same. Now this doesn't always happen. This happens when there are no external forces that are doing work on this thing. Now if some guy comes and starts playing with the ball, so here's me with extremely long arms, and I start playing with this ball, and I have 4 arms actually, or maybe I'm playing with my beard and the ball, then of course this is not going to happen anymore, because I'm going to give this ball energy with whatever I'm doing to it. But if there's no external forces, if nothing else is influencing this thing, then the mechanical energy is always the same. It's conserved. So for example, what happens when there's friction? Well, when there's friction, again, there is an external force. So what will happen is that this thing will lose some energy because of friction that's doing work against it. So for example, when things are falling through air, not all the potential energy gets turned into kinetic energy, because some of the energy is lost to the air. But if there's no air, or air resistance is very small, then mechanical energy again is conserved. It's always the same. So what is this useful for? Well, this is useful for calculating many things, and a typical example is a roller coaster. Okay, so imagine that I have a roller coaster that does something like that. Okay, and let's say that the red line signals 0 gram, and let's say that this is 2 meters, this is 10 meters, and this is 7 meters. And I have a little ball on top. So here's a ball. And it's still here. So then what I want to know is how fast this ball is going to be going when it reaches this point, and then this point, and then this point, and then this point. Now, if I did this with kinematics, with acceleration and all that stuff, I would go nuts. It would be very, very complicated. However, using energy, this is child's play. So that's why we do energy stuff, because calculating things like the speed of this ball when it reaches this becomes a matter of 1 line of problem instead of the 20 lines that it would be if we were doing this with kinematics. Okay, so now imagine that I have this ball here and it's still. So then I ask myself, okay, so what is kinetic energy? Well, first, actually, sorry, let me tell you that its mass is 2 kilos. Okay. So then I ask myself, at this point here, what is its kinetic energy? Let me zoom this out a little bit so that we can see the calculation. So let's label this point A. So this will be A, this will be B, C, and D. Okay, so at point A, how much is the kinetic energy? Well, the kinetic, if this thing is not moving, then 1/2 of mv squared, but v is 0, so 0. How much is the potential energy? Well, the potential energy is mgh. M is 2 kilos, g is always 10, and h in this case is also 10, because this guy is 10 meters up. So 10 times 10. So then we have 200 joules. So what is the total energy of this thing? Well, the total energy is the kinetic energy plus the potential energy, and that's 0 plus 200, that's equal to 200 joules. So the total energy is 200 joules. Good. So then let me ask you, how much is the total energy here? Pause the video and tell me. Good. Hopefully you did what I asked you, and you answered that 200 joules also, because the total energy does not change. Here, the potential energy is turned into kinetic, true, but the mechanical energy is the same. It's conserved from here and here. So here, we still have 200 joules. How about in C? How about in D? How much is the total energy? Pause the video and tell me. And now, hopefully, you also got that here is also 200 joules, and here is also 200 joules. Now, imagine that I want to know the speed of this thing at B first. So I ask myself, well, how do things work at V? Well, at B. So at B, the kinetic energy, I don't know how much it's going to be, but it's going to be 1/2 of mv squared. And m equals 2, so 1/2 of 2, that's 1, so it's equal to v squared. And the potential energy, because this thing is at the bottom, has to be 0 because H is 0, right? So potential energy equals mgh equals 0. So the total energy is V squared. And V squared is equal to the total energy, which we already said was 200 because it's the same here, 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 and here. Good. So V squared equals 200. And then this means that V equals the square root of 200. Done. And then if you want to put that in your calculator, go ahead and do it. I'm not going to do it. But the square root of 200 meters per second. Do you see how easy this was? And do you realize how hard this would have been if we had used kinematics? So this saves us work. This makes things way easier for us to calculate. What if I want to calculate things at point C? And I'm not going to do D because it's the same thing. So if I want to calculate things at point C, then again, kinetic energy will be 1/2 of mv squared. It won't be 0. It will have some speed here. So I don't know how much speed, but it will have some speed. So again, 1/2 of m, some speed I don't know. M is 2, so again, equal to v squared. And how about the potential energy? Well, in this case, I will have potential energy because this is not on the ground. This is here. It's at 2 meters. So potential energy is mgh equals 2 kilograms because that's m, times 10 because g is always 10, and then times 2 meters because h is 2 meters. So times 2, and that's equal to 40 joules. So then, how much is the total energy? Well, the total energy will be equal to the kinetic energy, which is v squared, plus the potential energy, which is 40, and that has to be equal to the total energy, which I calculated before, that has to be 200. So that's equal to 200. Now, as you know, this 40, I can put it in here, subtracting, so I get that v squared has to equal 160, and therefore we have that v has to equal the square root of 160, which is 4 square root of 10 meters per second. Done. So again, always the same principle. Total energy is conserved. I just need to find out how much potential energy I have in each place, how much kinetic energy I have in each place, make the total energies equal, and then I'm all good. One-line problem solved. I repeat, this using kinematics would have been a nightmare. Alright, so that was it for today. Now we're going to go through the learning objectives to make sure that we have learned everything we were supposed to. So first thing, know that energy and work are measured in joules. Well, hopefully at this point you know this, since you had to know this like a lesson ago. Know that objects may have energy due to their motion, kinetic, done, or to their position, potential, done. Know that mechanical energy is conserved in the absence of external forces. Remember, conserved, it means that it's always the same, but this only happens when there's no external forces acting on things. Now, recall and use the equations for kinetic and potential energy. Well, I've taught them to you. I don't know if you're going to recall them. I certainly hope so. Otherwise, make sure that you study them until they stick to your head. And finally, use energy conservation to solve simple problems, which is what we just did, and is what you're going to be doing over and over and over again the next lesson. Okay, so thank you very much for listening, and I will see you guys soon. Bye.